Hello everyone, and welcome to the scientific adventures of Beardman. Today we're going to be talking about nuclear fission, fusion, and radioactive decay. These are all important processes that take place in the nucleus of an atom. First, nuclear fission is the process of splitting a heavy nucleus, like uranium, into two more lighter nuclei. This process releases an enormous amount of energy in the form of heat and light. To put it in perspective, 1 kilogram of coal releases 8 kilowatt hours of energy, while 1 kilogram of uranium releases 24 million kilowatt hours of energy. Or to put it differently, in order to get the same amount of energy as the fusion of 1 kilogram of uranium, you would need to burn a mountain of coal, about 2.7 million kilograms of coal to be exact. That's enough coal to fill about 100 train cars. This huge difference in energy density is why nuclear power plants can generate so much electricity from a relatively small amount of fuel. Nuclear fusion is even more powerful than fission. When light nuclei, like hydrogen, fuse together, they release an incredible amount of energy. This is the process that powers the sun. Every second, the sun fuses millions of tons of hydrogen into helium, releasing the energy that makes life on Earth possible. And the sun is just one of billions of stars in our galaxy, each powered by fusion. Even more mind-blowing, when massive stars die, they explode in supernovas, events driven by runaway fusion that release more energy in an instant than our sun will in its entire lifetime. Scientists are working hard to recreate fusion here on Earth. If they succeed, it could provide us with a nearly limitless source of clean energy. You might be wondering where all this incredible energy comes from in fission and fusion. You might also be wondering why we get energy from splitting atoms and from putting atoms together. The answer lies in Einstein's famous equation, E equals mc squared, and a graph called the mass per nucleon. This equation tells us that energy, E, and mass, m, are actually different forms of the same thing, and they can be converted from one into the other. The c squared is the speed of light squared, which is a huge number, meaning that even a tiny amount of mass can be converted into a massive amount of energy. Now look at this graph. It shows the average mass per nucleon, protons and neutrons, for different atoms. Notice how it dips down in the middle. That's called the valley of stability. Iron is the element in the center of that valley. This will become very important when we look at the life cycle of stars in a future video. Atoms want to be in this valley. It's where they're the most stable. Heavy elements, like uranium, can become more stable by splitting apart, nuclear fission, and moving down the curve, releasing energy in the process. Light elements, like hydrogen, can fuse together, nuclear fusion, also moving down the curve and releasing energy. It's all about getting to a lower energy state. Now, let's talk about radioactive decay. Some isotopes have unstable nuclei. It's like the protons and neutrons inside are just not arranged in a way that they're happy with. To become more stable, these nuclei release energy and particles in a process called radioactive decay. The original unstable atom is called the parent isotope, and the atom it transforms into is called the daughter isotope. This decay process can happen in a few different ways, and it's happening all the time, even inside the Earth. Deep in the Earth's core, radioactive elements like uranium and thorium are constantly decaying, generating heat that keeps the core molten and drives many geological processes like volcanoes and earthquakes. It's estimated that radioactive decay produces about 20 terawatts of power within the Earth. That's about twice the amount of energy humans use globally. Now, let's look at the three most common types of radioactive decay. In alpha decay, an unstable nucleus emits an alpha particle, which is basically the same thing as a helium nucleus. 2 protons and 2 neutrons. Alpha particles are relatively heavy and have a low penetrating power, meaning they can be stopped by a sheet of paper or even your own skin. In beta decay, an unstable nucleus emits a beta particle, which is simply an electron. Beta particles are lighter than alpha particles and have a higher penetrating power. It takes a sheet of aluminum to stop them. In gamma decay, an unstable nucleus emits a gamma ray, which is a high-energy photon. Gamma rays have no mass and no charge, but they have the highest penetrating power of all. You need a thick layer of lead or concrete to block them. Radioactive decay can be used to determine the age of rocks. This is because the rate at which the radioactive isotope decays is constant. For example, uranium-238 decays into lead-206 with a half-life of 4.5 billion years. This means that in 4.5 billion years, half the uranium-238 in a sample will have turned into lead-206. By measuring the ratio of uranium-238 to lead-206 in a rock, scientists can calculate how long ago that rock formed. This method is especially useful for dating really old rocks, like those formed billions of years ago when the Earth was young. For example, these zircon crystals from the Jack Hills are approximately 51% uranium-238 and 49% lead-206, which makes them 4.4 billion years old. When zircon crystals are formed, uranium-238 is just the right size to fit nicely into a crystal lattice with zirconium-4 silicate. However, lead-206 is excluded from the crystalline lattice because the lead atoms are too small. So all the lead-206 that is in them now must have been formed during the decay process. Here's another example. Potassium-40 is a radioactive isotope that decays into argon-40, a gas. When a rock is molten, or liquid, any argon gas escapes. But once the rock solidifies, the argon-40 produced by the decay of potassium-40 gets trapped. So by measuring the amount of argon-40 in a volcanic rock, scientists can figure out how long ago that volcano erupted. This method is great for dating events that happened millions of years ago, like the formation of mountain ranges, or the ocean floor in situations like seafloor spreading. Nuclear fission, fusion, and radioactive decay are all incredibly powerful processes that take place in the nucleus of an atom. These processes have a major impact on our world, from powering our homes and businesses to providing the energy that drives the sun and stars and even shaping the very ground we stand on. I hope you enjoyed this video. If so, please click those like and subscribe buttons. If you have any questions, please leave a comment below. We look forward to seeing you soon here on the Scientific Adventures of Beardman.